Welcome back, everyone. Now that we've gone through the exercise of using a microcontroller in the Arduino environment to turn a microcontroller pin on and off, let's build an actual relay bypass module. So we'll go through the schematic, we'll go through the code, we will show it working on the breadboard, and then we'll create a PCB layout for it so that you can either go through the same process to design your own, or you can just use the files for this one to make your own. So to start with, I've got the schematic here, and I already have the schematic done, and we're going to talk through why each of the things are there. I decided not to walk through the steps of placing all the components to save some time, but let's go ahead and take a look at it. So down here we have our relay. Okay, now this doesn't have a traditional relay symbol because I got this symbol from Mouser, and sometimes when they create their symbols, they just create kind of this generic box package with the pins as opposed to using the traditional symbols that we would expect. But on our relay here, you can see that we have a coil plus and coil minus. We have our two common pins because this is a DP-DT relay. And then NC stands for normally closed, meaning that when no power is applied, pins 2 and 3 are connected and pins 6 and 7 are connected. And then normally open. And when we apply power, the common pin switches from normally closed to normally open, just like you would expect with a toggle switch. So with our relay here, you will notice that the normally closed on pin 2 goes to ground, and the FX in is on the common, and that the actual signal in to our box is coming in on the normally open pin. And so when power is applied, the input to the effect is going to go to the input that's coming into our box, but otherwise it's going to ground the effect input, which is good practice to minimize any kind of noise bleed through. And then our input is connected to the normally closed terminal on the second pole because the common terminal is our output, meaning that when no power is applied, our input to the box comes over to here and is connected to the output of the box. True bypass, okay? And then the effects out of the circuit board is going to be on the normally open pin. Okay, and then the only other thing to note here is we have this diode here. This is called a flyback diode. And the reason we have this flyback diode is because this coil that we apply power across to switch our contacts has an inductance where when we turn the relay off, it can create a negative voltage spike. And this diode protects our transistor over here from that negative voltage spike. All right, so that is the relay. Pretty simple. This is our microcontroller right here. We're going to use the ATtiny85. Because of how little memory space this takes, it could also be an ATtiny25 or an ATtiny45. They are all the same microcontroller, essentially, just with different amounts of memory storage. And a simple relay bypass program is not going to take up very much space at all. So, but I have plenty of the 85s on hand, and so that's what I just use by default. We can see that it lists all the various functions for each of our pins. We don't really need to worry about any of these because we're just using regular old digital inputs. We are going to have a pin change interrupt where our switch comes in. But other than that, we're only using 2 pins, one for the switch input, one to drive the relay. So, if you wanted to, you can add additional features to this, but we're going to keep it basic so that the code doesn't get really overly complex or anything like that. We do need a voltage regulator so that when we apply 9 volts from our circuit board, our effect circuit board, onto our relay bypass, we can provide the 5 volts necessary for our microcontroller and also the 5 volts for our relay. We're going to use a 5-volt relay. And so we feed 9 volts in. On the output, we have a large smoothing capacitor, and then this smaller capacitor, we put that in parallel because that is going to actually be placed right by the power pin of our microcontroller. It's called a power decoupling cap, and it just helps make sure that any like high frequency noise on the power line doesn't affect our microcontroller. Okay, and this is just a little tiny guy. All of these parts are surface mount so that we can make it really small. For our switch, you'll see that I've got my 2 terminals for my switch. One is connected to 5 volts and goes through a cap and is connected to this pin. But the pin is also connected through a 4.7K resistor that goes to the other switch terminal, and then there's a 47K resistor to ground. Now, this looks like a little bit of a complicated setup, but the way that it works is this. There's always power on this side of the switch, but this capacitor is blocking it, so that this pin, when the button is not pressed, all it sees is an equivalent 50K ohms, about 51.7K ohms to ground. So that's going to make sure that the voltage is pulled down on the pin. So the pin is going to be low whenever our button is not pressed. But as soon as we press our button, we then have 5 volts here, which is going to go through our 4.7K resistor and onto the pin, and it's going to both charge up this capacitor, and it's going to turn this pin high. And so with this resistor and capacitor, we're essentially forming a filter here to debounce the switch in hardware, so that any really high frequency flipping back and forth of the contacts from the contact bouncing on the switch is going to get smoothed out. So this is the hardware debouncing I talked about in the last video. And we're going to use this in conjunction with some software debouncing to give us the most predictable performance possible from pressing the switch. Okay, so that's the switch part. The last part of the schematic is how we're actually going to allow the relay to turn on. So when the switch gets pressed, we're going to read that the switch is high, and if it's debounced and we say that it needs to change state, then this pin will go high. Pin 2 will go high, and it's going to do 2 things. One is it's going to drive this LED through this resistor to ground. This is our indicator LED right here. Okay, and then it's also going to send the high voltage through a 4.7K resistor to the base of our transistor. And then it's got this 100K to ground, so that in the event so when this pin goes off, there is a path to ground for the pin to get pulled down to ground, so that it doesn't accidentally get left floating or at some kind of middling resistance that could result in unpredictable performance. Okay, so when we have our pin 2 go high, the voltage is going to come across our 4.7K resistor. It's going to hit the base of this transistor, and it's going to cause this transistor to conduct. And so this transistor is going to essentially look like a straight wire, and it's connected to the negative coil of our relay. 5 volts is always applied to the positive coil of our relay, but the negative coil of the relay, when pin 2 is low, is an open circuit. So there's no voltage drop across the coil. The relay does not turn on. But as soon as we apply enough voltage here on the base, it's going to cause the transistor to conduct. We're going to have a path from coil minus to ground, and all of a sudden the coil is going to conduct, and our relay state is going to change. All right, so this is a non-latching relay, meaning that as long as we have the effect enabled, this guy is going to be pulling some power. Okay, and this particular relay uses about 100 milliwatts of power, so it's about 20 milliamps at 5 volts that it's going to use to keep it on. So that is a consideration if you're daisy chaining a whole ton of pedals that have these on or something, is just, make sure that the draw of your pedal combined with the relay bypass module doesn't consume more power than your power supply can provide. But that is the entirety of the schematic. It's very basic and straightforward because we're not doing a whole lot in the hardware. We're simply sensing when a button gets pressed and reacting to it on this pin. Okay? Now let's take a look at our code that we're going to use for this bypass module. It is more involved than what we did last time because we're going to do a couple of things differently. The first thing that we're going to do is we are going to not only toggle the relay on and off when the button is pressed, but we're also going to allow for a momentary press and hold function where if the button is pressed for more than half a second, the relay will turn on, but when the button is released, it'll turn back off. So that way, if you just tap the button, it'll toggle the state of the effect, but if you press and hold, it will turn the effect on until you release the button. It can be really handy for effects that you just want for a little while in a portion of a song or something. The second thing that we're going to do that is different is we are going to use a pin change interrupt for sensing when the button is pressed instead of checking the button every single iteration of our loop. What that'll do is it'll actually make the code faster because the microcontroller is designed and made in such a way that when the flag for a pin change interrupt gets set, it stops everything else that it's doing and it goes and runs a routine that is the interrupt service routine to handle the change on that particular pin. And we'll talk about it a little more when we get to that section of the code. But we're just going to start here looking from the top of the code, and we'll just work our way through it. In this particular case, I have my relay on pin PB3, which is physical pin 2, and the button or the switch is connected to pin PB4, which is pin 3 of the physical package. That's the thing, is you have to keep track of what your Arduino package wants to see. So we're using the really common ATtiny package that I will get into that I will talk more about once we get through all the code, and it wants to know what the port B pin number is for our assignment. It doesn't care what the physical pin of the package is. It wants to know what is the pin that the hardware architecture sees. Okay? It has to do with how it handles all the registers internally. So we're going to initialize some stuff dealing with the relay and the button. Our relay state, we're just going to have it start low. Our button state, we're just going to define the variable and we'll worry about setting it later. And then the last button state, we're just going to, by default, we're just going to say the last button state was the button was not pressed. Okay? And all of these are uint8t type, which means it's an 8-bit integer, unsigned integer. And this takes up less space in the memory than something like a long. You can go read about data types to get all the scoop on that. I'm not going to really get into it, but the thing is that when you use an 8-bit integer, it's going to save more memory space in your chip. Okay? It's not a big concern for what we're doing here, but it's good practice to limit your data type to what you expect your information to actually be. So since the relay state, the button state, and the last button state are always going to be a 1 or a 0, then we can just set them as an 8-bit integer, or you can set them as a Boolean. But that's not something that I worry about. Usually I just use an unsigned integer. But for dealing with time anything that deals with time, I like to use a long because it uses more bits, and so it can actually keep track of the long timestamps that can happen as the microcontroller is running. So we've got the last debounce time, which is just keeping track of when did we last look at the switch for debouncing, the debounce delay in milliseconds. The last button down time is a timestamp that we use for determining when we first press the button and to see if we have kept the button pressed long enough for it to be a press and hold event instead of just a press event, okay? And then button press time, this defines how long we have to have the switch pressed down in order for it to say, oh, it's a press and hold and not just a press. This flag is going to get used for indicating whether or not the switch, when it changes state, is something that we want to deal with, and we'll explain that a little more later. And then the temp debounce state, like in our last in the last video, we're using this temp debounce state to keep track of the debouncing of the switch. It's just a temporary placeholder that gets constantly overwritten. So then we come into our setup function, and this gets run once when the relay power, or when the microcontroller powers up, if you remember. So our relay pin is an output, our button or our switch is an input. This relay we're going to write to low so that it starts off low, and this right here is not actually needed. That was a little debug statement that I had put in there. Not needed. Get rid of it. But now you see that we have some seemingly gibberish here. These are the configuration registers that are needed for telling the microcontroller that we want to do pin change interrupts. So GIMSK is the general interrupt mask, and when we set this particular bit to 1, it says enable pin change interrupts on port B. And then we have the pin change mask, and the pin change mask says, okay, which pins do we actually want to be pin change interruptible? And the way that the mask gets interpreted is that this is PB0, PB1, PB2, PB3, and PB4 right there, which our pin 4 is the one that we want. So this comment actually needs to be like that, because we want the switch to be a pin change interruptible pin, so that as soon as we press the button, it's going to go and run the interrupt routine. And then SEI is the command for starting the interrupt routine. Okay, that tells the microcontroller, take these guys in and start listening for any changes on, in our case, on this particular pin, and react to it when something happens. And what does it do when it happens? Well, that is what this function is for. ISR stands for interrupt service routine, and PCInt0vect is the register internal to the microcontroller that keeps the pin change interrupts status on it, so that when this gets set, when anything in here goes high, that means, hey, there's been a pin change event on one of the pins that I'm listening to. And so what we want to do in an interrupt service routine is keep it as short as possible, because it's meant to execute very, very fast. And so what we're going to do is we're going to read the button. And if the reading of the button is not the same as the last button state that we had, then we're going to say, all right, this looks like we have a change of state to our button that we're interested in. So we set the temp debounce state to the reading so that other functions can access this variable, and we're going to set the flag to 1. And the reason why we set this flag to 1 is because when we come into our main loop, we're not going to do anything until the button is pressed. right? We're basically just going to sit back and wait until the button gets pressed, and as soon as the button gets pressed, we're going to react to it really, really fast so that there's as little latency as possible. So if the flag is not 0, if the flag is 1, then we're going to check the button. But if the flag is 0, then we're not going to bother checking the button, and we're just going to wait for the flag to come back. Okay? So check button is the function that gets called from our main loop, and we'll look at it right here. This check button is going to combine the debouncing of the switch as well as handling whether we have a low to high transition, meaning that the button has been pressed, or if we have a high to low transition, which means that the button has been released, and if the button has been released, we check to see if it has been long enough to be considered a press and hold. So the way that this works is we say if millis minus the last debounce time is more than debounce delay. So if we have waited long enough for it to meet our debounce delay, then we're going to do another check, and that is if the button is the same as our temp debounce state that was set up here, then that means that after debouncing, it's a stable reading, so we're going to do something with it. And so we set the button state to the temp debounce state because we say it's been debounced, so we're going to update our button state, and then we're going to do another check. If our button state is low and the last button state was high, then we have a high to low transition, okay? And what we're going to do is we're going to toggle the relay state, and we are going to mark the last time that the button was held down, okay? Now, if that's not the case, well, even if that is the case, we're going to run this check, and if the button state is high, and the last button state was low, and our millis minus last button down time is greater than the button press time, so what this means is we have a transition where the button has been released, and the last button press was that the button was high, so we have an on to off transition, and it's been long enough that we have exceeded last button press time. This means that we have pressed and held the button long enough for it to be a button press, and we've lifted our foot off. So we hard set the relay state to low in that case. All right? And then we write to the relay state. So up here, this is handling the toggling. This right here is handling the press and hold release. And then we're updating the relay state, and then we update the last button state to be button state so that we can use that for comparing next time. And then we set our flag to 0, okay? Because this means that, all right, we have now waited long enough for it to be debounced, so we can set our flag back to 0. The reason we don't set the flag back to 0 if we have not exceeded the debounce delay is we don't want the contacts of the switch bouncing to trigger our interrupt service routine while we're still doing something. Okay, so we lock this flag out until after our debounce delay has been exceeded, and we've had a chance to figure out if we actually had a real button press or not. Okay? And so we set this flag back to 0, which then means that we are then ready for the interrupt service routine to happen again. Okay? So that's the entirety of the code. Hopefully that makes a little bit of sense of what's going on here. If you don't have a lot of experience with code, I would recommend that you download the code and take a close look at it and Google around. The Arduino documentation is very thorough about everything. So if you want to look at data types or how the different loops work or things like that, there's tons of information on it. So the next step is going to be going over to the bench and putting the circuit on the breadboard and making sure that it behaves the way that we want.